Thank you. Good morning, everyone. Thank you for coming to our hands-on tutorial session. My name is Catherine Zhao. I am a data scientist at Microsoft, working on the end-to-end scalable data analytics solutions with Microsoft technologies. In the next 3 hours, my colleagues and I will walk you through the scalable data analytics using R, from single machines to Spark clusters. And before we get started, the tutorial material, you can find it in the tinyurl.com/kdd2016R, all uppercase. And you will also get a paperclip with all the login information, your cluster information. Each one of you will get a cluster for yourself, which later we will use in the hands-on session. And you should have your own password. And the login username will be the remote user. And in today's tutorial, we'll cover an introduction of scaling your R script, a hands-on tutorial of end-to-end scalable data analytics solutions, some practical examples and case studies, and the remaining time at the end, we will leave it to the Q&A session. So I will cover the introduction part. In the introduction, we'll be answering these 4 questions. What is R? What limits the scalability of the R script? What functions and what functions and techniques can be used to overcome those limits? And how do the base and the scalable approaches compare? So before we start, how many of you used R before? Oh, awesome. So then you already know basically what is R. Just in case some folks haven't get a chance to experience with R, R is the most popular statistical programming language. It also can be used as a data visualization tool. And within the community, it has over 2.5 million users, and right now most universities are teaching R in the classroom, and students are using it for their projects. And basically, R has wrapped its user group worldwide. Now, R has over 8,000 packages and has been well integrated with many applications and platforms. In the most recent IEEE Spectrum rating of the top 10 programming language, R has followed its momentum from the past years and moved up to the top 5. So right now, the top 5 programming language on the market are C, Java, Python, C++, and R. Another interesting survey made by Birchworks also shows the popularity of R. So for over 1,000 respondents, 42% of them use R over SAS or Python for their analytics work. R also has been used across multiple verticals in either academia or on the industry, such as retail, financial services, healthcare, and manufacturing. Some of the common use cases are demand forecasting, customer churn, fraud detection, or etc. Although R is very popular in practice, we often heard there are some challenges within our community in terms of its scalability. The first challenge is in-memory operation, because R behaves to load all the objects into memory, which could easily cause the out-of-memory issue when we're handling big data. R also has expensive data movements and duplication, because R intends to copy an object instead of referring to them by default, which could also blow up the memory too. Lastly, lack of parallelism. R by default is a one-threaded programming language, which means it will execute a one-core, multi-core machine. Also, the open source R is not enterprise class either because of its inadequacy of community support, lack of guaranteed support timelines, no SLAs or support models. But there are many scalable R solutions in the community or out on the market. That's what we are going to cover today. We can choose some R packages with big data support on single machines, such as the Big Memory Project, FF, and related packages. We also could use some scalable solutions to help us scale from single machines to distributed computing on the clusters, such as the Sparklier, Rebel Scale R, and more packages. So the Big Memory Project was coined by Michael King and John Emerson at Yale University. It was aiming to work with massive matrix-like objects in R. The big memory combines the memory and the fallback data structures and create an object called the big matrix. So a big matrix can allows users to easily manage and analyze the data set which is larger than the available RAM on their machine. And big matrix is basically a pointer to the code data structure that written in the C++. This particular data structure can also be allocated to the shared memory, which allows the separate processors on the same machine can share access to a same data set. With this reference approach, big memory brings a smaller object into the memory. In this particular example of importing 20 million rows and 26 columns numerical matrix by using the big memory package, we can see the big matrix objects only takes 600 bytes on the memory. But if we convert it to its corresponding R matrix, then it will end up taking 2 gigabytes of the memory. And think about if you have a larger matrix, then that could cause the out-of-memory problem in this case. The big memory package is also the core of this particular project, which also contains a set of sister packages that to extend the analytics functionality, such as Big Analytics provides explanatory data analysis. Big Tablets adds a table, t-apply, and split-like behaviors for the big matrix objects. A big algebra performs a linear algebra calculation on both the big matrix and the R matrix, and synchronicity gives the support for the synchronization. And some of the other packages also use a big matrix as their data structure to provide linear and the GLM models on top, such as the big LM package, or enable the shared memory parallelism with a big matrix object, such as the RDSM package. As we finish up with the big memory projects, the FF package is also another way to help us scale on the single machines. It was designed to provide convenient access to the large data from persistent storage. So in the storage, FF objects store the raw data in naive binary flat files. Only a small part of the data will be mirrored into the main memory for its effective computation. And like the big memory project we talked earlier, this FF package accepts both numerical and categorical data as the input data set. As I mentioned earlier before, the all objects makes multiple copies by their value in the RAM, which are causing the problem for out of the memory. To overcome these particular limits, the FF data frames separate the vertical layouts from their physical storage So the actual objects are stored in the disk and virtually mapped into the memory in the file system cache. But they can quickly accessible through its FF technologies. FF also raised a lot of related works and packages such as FFBase at the basic statistic functionalities. It provides the data coercion, selections, aggregation. It also leverages the linear models from the Big Memory project. And DeepLiar is another package on top of FF, provides a linear angle regression, lasso, and stepwise regression. As we have gone through how to scale our R script on the single machines, let's now see how we can what kind of solutions can help us from single machines to distributed computing on the clusters. Scale on the Spark cluster is one of those approaches, and that's what we are going to focus today. Spark data frame is conceptually equivalent to the tables in the relational database or the data frames in the R objects. So if you are familiar with Spark, then you can think the Spark data frame can be think as a RDD plus a schema. With the SQL context, Spark R can create a Spark data frame from local R data frames, CSV, JSON, packet files. Using the Hive context, it can also access to the Hive meta store. And the Spark R 1.6 is pre-configured on the Spark clusters in the HD Insight. So you don't need additional installation if you use the Spark clusters in HD Insight. Spark R supports functionalities for structured data processing, such as the data selection and aggregation. It also, in the new version, the Spark R 2.0, it also allows applying the user-defined function on each partition of the Spark data frame. Spark R, for machine learning purpose, Spark R uses the Spark machine learning library MLlib to fit the GLM models. And in the Spark R 2.0, more algorithms such as the survival models, naive Bayes, k-means, and the model persistence are included in there as well. The next package I want to introduce is called the Sparklier. It is another R interface for Apache Spark. So on top of the Spark engine, Sparklier has three main components: the DeepLiar, machine learning, and the extension to call the full Spark API. It can be easily installed by using the dive tool from the RStudio/Sparklier if you want to try it out later, and we will also walk you through it with details in the hands-on session about this package. It helps you to connect to both local instances of Spark and the remote Spark clusters. And you can easily switch which Spark cluster you want to connect it in the connection string. Like the Spark R package we talked about earlier, it also loads data into the Spark data frame from the different data sources. Sparklier provides a completed data backend for the DeepLiar backend for data manipulation, analysis, and visualization. If you are not familiar with DeepLiar, it provides an easy data manipulation pipeline through this PEP operator. And in the machine learning, there are three family of functions for machine learning pipelines also being included in the Spire. So ML functions provide machine learning algorithms such as k-means, random forest, multi-perceptron. FT functions provides the data transformation for each individual features. SDF functions provides the data manipulation for the Spark data frames. Lastly, the Microsoft R server can also help to scale out R, and it's truly enterprise class. It is 100% compatible with the open source R, which means whatever the codes and packages that you are working on today, it can be directly work in the R server. It also has ability to parallelize any R functions, which is ideal for the data science process, such as the parameter sweeping, simulation, and scoring. It provides a wide range of scalable and distributed Rx prefix functions, such as Rx data set for the data transformation. Rx summary gives you basic statistics, a lot of machine learning algorithms, and to set the compute context for the parallelism. We will use some of those functions in our hands-on session later. In the next slide, you will see a full list of parallelized and distributed analytics provided by the R server. So R server works on end-to-end data processing, analytics, and modeling. It provides the functions for ETL, statistics, machine learning, simulation, and customized parallelism. R server is a set of technologies that is portable across multiple platforms. There are four key components within the R server. The scale R, as we talked earlier, it provides a distributed and parallelized analytics. A connect R has a high-speed and direct connect to various data sources, such as HDFS, Teradata, SAS, and etc. Distributed R includes a distributed computing framework, which supports cross-platform functionalities. And lastly, the deploy R can deploy your analytics as a web service in any platform or backend system. In terms of the portability, the Revolution R, Revel Scale R works in clouds, Hadoop, Spark clusters, data warehouse, desktop, and servers. In order to scale, let's see how Microsoft R handle the big data. As the big data comes in, the data has been partitioned into different chunks, and the data will be sent to the different cores on the compute nodes. Within each compute nodes, the scale R algorithms work in parallel at high speed, and the interim results are collected and consolidated analytically to provide the outputs on the entire data sets. XDF data format is a new data format that can significantly speed up the iterative algorithm processing. Another important concept of Microsoft R I want to emphasize is write once and deploy anywhere, which means the scale R models can be deployed in either the Spark or Hadoop clusters without recoding any functional R models. Let's see an example here. So the compute context of R script can set where the model will run. So for example, if you run the model in a Linux or Windows machines, then we can set the compute context as local parallel and the data file system as a local directory. If we run the models in the Spark or Hadoop cluster, the only thing that we need to change is setting the compute context to RxSpark or Hadoop MapReduce, the file system to the HDFS file system. As we can see here, the functionality script in R for statistical analysis, modeling, and visualization will remain the same no matter where the model runs, either in the local machine or on the cluster. As we have already talked about the different approaches to scale our R scripts, let's see a comparison between the base and the scalable approaches here. So for the CRAM-R by default, the big memory and FF project can help us to scale the packages, to scale our R script in single machines. Sparklier, and the Bravo Scale R can also help us to scale up as a distributed computing in the clusters. The distributed computing solutions support Spark, for sure, and Bravo Scale R from Microsoft also can run on Hadoop clusters for the MapReduce job. And the last three packages all works with SQL compute context too. And the Bravo Scale R provides the connections to Teradata as well. And it provides the enterprise supports over the community supports for the enterprise solutions. As we have already talked about all those different approaches, you are probably wondering how fast and scalable those approaches could be. Let me show you an example here of the execution time running logistic regression model from end to end by using the CRAM-R, Microsoft R server on Spark, Spark-R, and the Sparklier. This is not a benchmarking, but it actually shows the R server on Spark is faster and more scalable. So the Microsoft R server on Spark is light green lines here. And the CRAM-R is the dark green lines in the bottom. And Spark-R is the blue lines in these charts. And the orange lines represent a Sparklier. So as we can see in this plot, the CRAM-R is not able to handle the handle the process if we increase the number of rows over 50 million of rows, so which it stops here actually. But Microsoft R on Spark can take much more data sets as the CRAM-R. Also, MRS on Spark has a smallest execution time, especially when we increase the data set. The second plot helps us to understand why the MRS on Spark is substantially faster than other approaches. As we can easily see in this plot, the execution model process for MRS is definitely a big gain. It takes a very small amount of time for execute models if the data is stored as XDF datasets. So now you already have a very good knowledge about different scalable R solutions. We will move on to the hands-on session, and Mario, my colleague, will walk you through how to solve a flight delay prediction use case use Microsoft R on Spark and the Spark R. With that, I can take any questions if you may have. Pardon me, can I?
For the R integration into Spark,
Mm-hmm.
done through R Java.
I think I could probably
Yeah, I think
answer
Mario
that.
can take that question.
No, we're not using R Java.
Mm-hmm.
Yeah. Mm-hmm.
Sure.
The integration, so you can invoke Spark. So it depends on whether you're talking about, we can actually run using Hadoop MapReduce or using Spark in a cluster. But when it's integrating with Spark, we have actually written some Scala classes that are implementing Spark classes. And then we're communicating with the with that process. So basically, there's communication between the R process, which is a C++ program, and the Spark process, the Spark driver process, which is a Java program. But they're not running in the same process, and we're not using R Java. Yeah. Yes, we're using named pipes. Yeah. Mm-hmm. Yeah. Thanks.
Yes.
You mentioned that the R server
Yeah, so it's basically 100% compatible with R. So whatever the R script that you have now, so you can think the R server has another set of R functions on top of the existing R functions. So it just helps you to do the distributed and parallel analytics. But whatever the functions that you're using today, you don't need to do any kind of encoding. It will work fine.
Okay, but it doesn't mean that all functions are able to take advantage of running parallel.
So we have Rx exact functions can allows you to take the existing R functions and running in parallel. And you will also learn that in the hands-on session too.
All functions? Like I'm just
Sure, everyone can hear, and it is being recorded, so questions, ideally we can use the microphone for questions, or we can repeat what folks say.
So basically the question here is whether the R server can take any R functions running in parallel. So we have a mechanism in the R server called the Rx exact. So that is a function can help you to scale your R script or R functions and running in parallel. So it does take, so that's the way that we're doing the parallel computing for other R packages or R functions. And you will learn this particular methods in the hands-on session, and you will see how it actually works. Any other question?
Can you use microphones if possible? Well, it's being recorded, so we'll have to repeat the question.
Do your packages work also in Spark 2.0?
Spark 2.0, shall I answer that, Catherine?
Sure.
Yeah, right now we're running in Spark 1.6.
Yeah.
We will be.
Okay, doesn't mean, okay.
Yeah, yeah. Spark 2.0 just became generally available a couple weeks ago, so we're not on that one yet. I see a question back there.
You showed some performance benchmarks with regard to logistic regression in R, so the R world, but how does it compare to maybe an MLlib logistic regression?
Answer that.
Yeah, sure. So this one, so basically the Spark R, let me go up here. So the Spark R is using the MLlib for the machine learning. So I'm basically, this particular comparison is using the MLlib functions, the logistic regression using in the Spark R. So as you can see, the Spark R and Sparklier are using the MLlib. And the Microsoft R is using our internal logistic regression models. And that's the performance comparison that we worked on before. Does that answer your question? Great. Any more question we can take here?
Are the slides online available, or will
Yes.
they be?
So it's /KDD2016R. So tinyurl.com/KDD2016R. And you will go to, it's
We
now showing
don't
up.
have the PowerPoint there, but we can. Oh, you did?
Yeah,
Oh, great.
I uploaded this morning.
Oh, fine.
So I'll double check and make sure the slides is there and accessible. So I'll hand it over
All
to
right.
Mario, and Mario walk you through the hands-on sessions. Thank you, Mario.
Thanks, Catherine. So I'm Mario Inchiosa, also at Microsoft, working on the integration of Microsoft R Server with Spark and other big data platforms. I joined Microsoft last year, was working as the chief scientist at Revolution Analytics, and in the year and a half now that we've been at Microsoft, we've been integrating our Microsoft R Server with a number of Microsoft systems, including HD Insight, and we've also introduced a new release on-premise in HD Insight in Hadoop clusters, Cloudera, MapReduce, MapR, and Hortonworks clusters. So I just have a couple more slides to set up the hands-on part that then we'll get a chance to actually run some code. So what does the architecture of our system look like when it's running in a Hadoop cluster? And in particular, I'm looking here at how it looks in the cloud when we're using HD Insight. So we can run, we start with an R process on the edge, on so-called edge node of the cluster. And this is, we're going to refer to this as the master process. Now, if you have a relatively small amount of data, you can do your processing on this edge node using the master process. And you just basically copy or stream data from the data that's in distributed storage to this master R process running on the edge node. And that is called local processing. And then to scale to larger data, you can use distributed processing. With distributed processing, you have a master R process on the edge node once again. But that master process is going to use Apache Yarn and Spark to spin up and communicate with worker R processes that are on the data nodes of the cluster. And each worker process will process when we're running one of our distributed algorithms, a worker process will process a portion of the data, produce an intermediate result. Those intermediate results will then be combined by a reducer and returned back to the master process as a final result for that iteration or that pass over the data. And then the master process, depending on the algorithm, will either return results back to the user or initiate another iteration over the data. And just one more graph showing scalability here. This really does scale to literally hundreds of nodes and billions of rows and terabytes of data. As you can see from the plot here, this is a logistic regression where we actually had to duplicate the New York City taxi data to make it bigger. So we could take it out to over 2 terabytes, and you can see it scaling, scaling nicely with number of rows. Number of rows is on the horizontal axis, and elapsed time is on the vertical axis. So in order to demonstrate use of this from end to end, I'm going to go through a typical advanced analytics lifecycle, where we're going to start with preparation of the data, which involves cleaning of the data, transforming, and also we can do big data joins in this preparation step. And then the middle step is modeling, where we will apply and train machine learning models based on the data we prepared. And then finally, operationalization, where we will take those models and deploy them so that they can be used for scoring. The specific case, as Catherine mentioned, is airline arrival delay prediction case. And I'm going to use a variety of technologies for those 3 boxes, the 3 steps. For the cleaning and joining step, I'm going to use the Spark R package, which is a package that's included in Apache Spark, providing access to Spark functions like the ability to do joins. Then I will be moving on to the second box, which is the training, scoring, and evaluating, and I'll be using the scalable R functions that are built into our server for that. And then finally, the deployment of a web service, as well as the consumption of a web service, will be done using the Azure ML package, another R package that we've contributed to CRAN. So the data set, well, there will be 2 data sets because we will be joining 2 data sets. The first is the airline data set, which is passenger flight on-time performance data, which is over 20 years of data, although for the purposes of the hands-on demo, we're using a subset of the data because we have created, everyone has, basically will get an HD Insight cluster with 2 worker nodes. So 2 worker nodes is not really enough to do the full data set in a quick fashion where we don't want to spend too many minutes per step here. So we'll use a subset. Same thing with the weather data. It's NOAA land-based weather observations from over 2,000 weather stations. So now I'll move into the cluster. We've already provisioned the clusters for you. If there's time, I'll show you the website that's used for provisioning a cluster. But let me move on to the hands-on portion. And the first step to get onto the cluster, I don't know, how many of you have already logged into the cluster at this point? So pretty much everyone has done that first step. I will do it now. I'm on a Windows machine here, so I'm going to use plink.exe as a simple way to create the SSH port forwarding to the cluster. So if you haven't done this already, do go ahead and create your SSH connection. Raise your hand if you have any trouble with this connecting. There are several folks in the room who can help you make the connection. And I will point out that the web page that we've been mentioning, this web page that is accessed by that tiny URL address has here instructions on connecting to the tutorial clusters. So you can see there in that section there's an SSH command if you're on a Linux or Mac machine, and a plink.exe command if you're on a Windows machine. So I will go ahead and initiate that connection and type in the password. Everyone has a unique password for this hands-on exercise, because we're all using different clusters. So now I have the SSH tunnel, and I'm going to point my web browser at localhost:8787. That will allow us to connect to our studio server, which is running on an edge node of the cluster. And when you, oh, yes, okay. I've already connected a few minutes ago, so it cached my password. But yeah, when you go to localhost:8787, you will enter username remote user. Everyone is remote user. And the password is the password written on the slip of paper that you received when you came in. If you're timing out when you're trying to connect, it could be that the SSH port forwarding is not active, so make sure you have the -L localhost:8787 localhost:8787 in your SSH command. Did that help? Or if okay, there's several folks in the room who are walking around to help if you do have a problem connecting. So everyone should get to our studio so that you'll be able to go through the scripts. Now, the first script is going to be in a directory called code. Actually, all the scripts are under the directory called code. So in the file browser in our studio, click on code. And then first demo is the one that's called MRS for Microsoft R Server. It's the second one in the list of directories under code. So I'm clicking on MRS for Microsoft R Server. And the first script that I will run is called one-clean-join. So just click on script 1.
Where should we start RStudio? Is it local or is it on?
RStudio is shown in your web browser, but it's running on the edge node of a cluster in the cloud. Okay. Yeah.
Go to the browser.
You do need to go to the browser, yes. This browser window is pointing at localhost:8787, which is connecting to the cluster via that SSH command we ran. The passwords are on the slip of paper that was handed to you when you went into the room. Okay, so the script 1 for cleaning and joining, the first thing it does is it sets the working directory. And the way you can execute each line in RStudio is just to put your cursor on the line and then hit Control-Enter. And that will execute the line. You'll see it echoed down in the console window. It'll also move the cursor to the next line. So it's very easy. You can just hit Control-Enter repeatedly, and it will execute the lines in your script. Also, if you wanted to run the whole script in one batch, you could click on the source menu and you could say source with echo. That would just run the whole script from beginning to end, which would take a couple of minutes. But I'd like to go through it in a little more detail. So I'll do it line by line. So the second line is sourcing the setComputeContext.r. And we'll take a quick look at this setComputeContext.r file. What that does is it tells RStudio where we want the computation to be done. Because I showed in my first slide that the computation could either be done entirely on the edge node using local processing, or it can be done as a distributed computation. And you have that choice depending on the size of your data and your use case. So when we want to do a calculation with our server, we specify where we want the computation to be done, and we specify where we want the data, where's the data that we're using. And when we're doing the computation using Spark or Hadoop MapReduce, then the data should be in the HDFS compatible distributed file system. So in that case, the setComputeContext.r will run this command which sets the file system to RX HDFS file system. That points us to the HDFS file system.
Sorry, where is this file located?
The script I'm using is located on the edge node of the cluster. So once you've created once you've run the steps of connecting to the cluster, it'll be in the code directory, and then under code go to MRS. Yeah, perfect. So we're going to choose where the data is located, HDFS file system. If we had wanted to use data in the local file system, we would say we could either leave it at the default, or we could use the RX native file system function to specify reading data from the native file system. And then when we want to use distributed computing using Spark, we specify the compute context to be RX Spark. If we want to use local processing or single node computing, then we specify what we call the compute context to be RX local SEQ. And see a hand raised?
Yeah, in RStudio, where is it going files?
Okay, in RStudio, go to open files. The easiest way is to go to the files window and just click on the file you want to open. Yeah. So this is in the MRS directory, yeah. Here is showing the directory path home, code, MRS. Once you're in the MRS directory, all of the scripts for my portion will be located in that directory. All right. So going back to the clean join script, we're going to specify the path to the Spark-R package, which is included in Apache Spark. We add that to R's libpaths, and we load that library. So now we've loaded the Spark-R library. And the next lines are going to specify to Spark that we want to use 10 executor instances, up to 10 if there's enough memory. And we specify how much memory we want to provide to the R process that's running under Spark. So if you had an R process that was loading a lot of data into memory, you could adjust this memory overhead setting. Next, we will call Spark-R init. And what that's going to do is it's going to start a number of Spark executors across the cluster, which will all be ready to, they'll all be Java virtual machines that are spun up and are ready to take commands and execute our computations. So one thing about Spark-R is that you run the Spark-R init command, that starts to claim cluster resources for you. And now those resources are held by you whether you're using them or not. So if you're in a big shared cluster, it's something to be aware of, that you are holding onto those resources until you call until you exit R or call Spark-R's close function, which we'll see later in the script. So there's one more init function we have to call to fully enable the Spark-R package, which is the Spark-R SQL.init function. And now Spark-R is initialized. And the next two lines we'll just define the path in the HDFS file system to the airline data and the weather data. We're just setting a couple of R variables there. And now we're going to use Spark-R's function for reading data, which is the read.df function. So this will read data that's in a series of CSV files will be read into Spark's in-memory storage. So I'll execute that. That'll take a moment because it's actually reading all of the data, and it is also inferring a schema from the data. So it does have to scan all the data. It's not just looking at the first few lines. And it's reading it from the distributed storage. We will also run read.df to read in the weather data. Question up here? You execute one line by either highlighting it and hitting Control-Enter, or simply putting the cursor anywhere in the line. And when you put the cursor in the line and hit Control-Enter, it will process that line and move to the next line. SparkR does use lazy evaluation, and we're going to see that. The next whole bunch of lines in the script are going to run with almost no delay because of the lazy evaluation. Yes. So the read.df is not lazy, especially when you say infer schema equals true, because you really got to look at the data to infer the schema. So next I'm going to do some cleaning and transformation of the data. And I'm going to rename some columns as my first transformation. So I'll use SparkR's rename function. I'll enter that, and that's done already. So that was lazy evaluation. I'm just instructing it that I want to change those names, and pretty much doesn't have to do any hard work. I'm also going to select columns. I don't want to use all of the columns. I want to use a subset of the columns. So I specify that using SparkR's select function. So that's specified as subset of the columns. Now I can do some simple math operations across all of the data using SparkR. In this case, I'm going to round down the departure time. I'm going to take the departure time, divide it by 100, and apply the floor function. And that will also happen instantly. So all lazy evaluation. We haven't asked it to print out any data or write out any data, so this is still lazy evaluation. Next, we're going to do some a little more complicated SparkR function. We're going to do an aggregation by date and time and airport. And what this is doing is it's aggregating the weather data so that we have one weather data value per hour at each airport. If there were multiple readings in 1 hour, it would aggregate those and average them. So I'll hit enter. That again, instantaneous response because it's really lazy evaluation. It doesn't actually do the calculation yet. I'm doing some more renaming. I renamed columns in the airline data set. Now I'm going to rename columns in the weather data set. And now I'm going to do the join of the airline data with the weather data. And in this join, I'm using SparkR's join function. And I'm joining the weather data at the origin of a flight, at the origin airport for the flight. So that's the first join I'm going to do. And then I also want to do, there's some more dropping of, sorry? Oh, you're getting an error on the aggregation. Try rerunning the lines maybe. Now I'm doing rename. Now I'm going to do a second join because we want both the weather at the origin airport and the destination airport. That'll help us make our prediction about arrival delay. So I'm going to join at the, do a second join where the join is based on the destination airport ID. And finally, I will do some more removing of redundant columns and renaming of columns. And now we're going to output this to CSV. It's all this basically has been instructions to Spark as to what to do with the data that's got in memory right now. I'm going to use the SparkR repartition function to specify that I'm going to want to have 16 CSV files. So you can adjust this based on the size of your data, how much parallelism you want. So here I'm going to select 16. And then I'm going to ask Spark to write the results to a directory of CSV files. And this is where the lazy evaluation now ends because we're actually writing the results to disk. So now it actually has to do the work that you've been asking for up to this point. So this is where a Spark job will run, and it will take a minute or two to perform this this join and transformation.
Quick question.
Yes.
Can you make the code look a little bit more like Scala by using the pipe?
Yes, you can use the pipe, R's pipe. Yes, if you use the Magritte package in R, and then you can use the % greater than % to make a lot of these look like pipes. Yeah. Yeah. Okay, it's finished the writing. So now we're actually done using the SparkR package, and I can run the sparkr.stop function, which will return those resources back to the cluster that it was holding on to. So we can use those resources for other purposes. And next lines remove the success file. Some of you who have been using Hadoop for a while may know that sometimes there's a success file written in the output directory. And we just want CSV files in our output directory. We don't want the success file there. So I remove that with a command we have in our server, rx hadoop remove. So we have a set of functions that allow you to access the HDFS file system easily from R. So now that we have those joined CSV files, I'm going to load them into a binary format that is very efficient for use with our server. We call it XDF. And to do that loading, I'm going to specify the schema of the CSV files. You can also infer the schema, but it's best to specify the schema yourself so you can really specify like whether you want a float or a double and exactly how you want the columns interpreted. So I'm specifying that schema. Now I'm specifying the data source. The data source for this operation is going to be text files. I'm reading in the CSV files that I wrote out with SparkR, and I'm writing them in our XDF format. So I'm specifying our output source is going to be RxXDF data, this data format that we use similar to Parquet in some ways. It's an efficient binary format. And then the Rx import function is used to read the data into this binary format, which is compressed, by the way, so it's also quite a bit smaller.
So file system are all those files? Is there a separate CSV for each partition?
The question was whether there's a separate CSV for each partition. It depends on the size of the CSV. The partitions are just, well, they're determined in. Basically, yes, it's basically, if they're not very large CSVs, there will be a separate partition for each CSV. If they're very large CSVs, they'll be split automatically because they can be split on new line boundaries. The question was, it's kind of about tuning of the calculation and dividing your data, how the parallel system divides your data into partitions. And tuning, we have default values that work, as useful defaults. But when you're working with a large amount of data, you may need to pay a little more attention to exactly how you partition the data. So there is documentation online we have for this tuning, the various knobs you have at your control for determining exactly how your data is divided. So the import has finished now, and now we can run the rxGetInfo function, which will read the metadata from this binary file format, the XDF format, and it'll tell us things about our data set. So we'll get to see, for example, how many files are in the data set that we created, how many observations, how many variables, and what are their types. And if I expand the output window here, you can see that information, like it's listing all the variables, and since it's recorded the high and low values for the variables if they're continuous variables, and if they are factor variables with categorical levels, then it will tell you, for example, destination airport ID has 295 levels. So there are 295 different destination airports in this data set. So that completes the cleaning and joining step. And now I'm going to go on to the training and testing set. Yeah.
These are functions that are specific for this file type. They're similar.
Okay. The functions, the question was, are these functions specific to the file type we're using? They're actually not specific to the file type. The functions that we're using, such as the, well, actually we haven't got, we'll see some more examples of the functions. The functions like that I'll be using for transforming data and performing logistic regression, those functions take a variety of data sources and work in a variety of these so-called compute contexts. Yeah, so data can be in text format, it can also be in binary format. Okay, so I'm going on to, yes. Okay, yeah. So I'm now moving on to the second script. Has everyone managed to get through the first script? I see some thumbs up.
I walked in late, so what is the first script? I mean, I'm on your GitHub.
Okay.
How are you numbering?
So we have a few folks who can help if you did come in late to catch up. And I see one hand up in the front row. Maybe you need some help. So did you need some help in the front row? Okay. Or was it a question or just help? Okay. Help. Okay. Tomasz, my colleague in the red shirt, is running around to help folks graciously, helping us out with the tutorial. So now we'll move on to script 2, which is going to be the training and testing. And again, I put the same 2 lines at the beginning of the script to set the working directory and to source the setComputeContext.r. I did that so that I could run these 2 scripts independently if I wanted to. So now I'm going to specify that the data I want to work with is the XDF data that I prepared in the previous script, and I'm going to split it into training and test sets. So to do that, I'm going to be using the RxDataStep function, which is a very general function we have for transforming data and also splitting it or selecting rows. And you can see in lines 14 and 15 that what I'm doing here is I'm selecting the rows where the year is not 2012. So in my subset of data, I have 2 years, 2011 and 2012. So I'll do training with the 2011 data, and I'll use that to predict the 2012 data. The 2012 data will be my testing data. So I'm running the RxDataStep function now that's going to create the training subset. And I will also ask it to run another RxDataStep function to split out the testing set. In this case, the criteria will be that the year equals 2012. So all the 2012 examples will be my testing set. And you can see Spark is printing out some information there. You can see the progress it's making as it's processing the data. There's a % complete shown there. And it's just finished the training, and now it's going to go on to the testing data, splitting that out. Now, if you want to monitor things on your cluster, I can show that quickly. We can go to the portal, the Azure portal. This is where you can create clusters and you can monitor them. And we've created the clusters for you in advance, so you don't have to go to the portal yourself. But if you were wanting to create your own cluster, you would go to the portal and you would click on the new button, and you would fill out about one screen of information of details that you wanted to specify how many nodes would be in the cluster, and what you want to name the cluster, and whether or not you wanted to have our server installed on all the nodes of the cluster, which we're using in this tutorial. Once you've created a cluster, you'll be presented with a dashboard And you have the ability to scale the cluster. So if you created a small cluster and then realize you want to have a larger cluster, you can click on the scale cluster and add nodes to the cluster. And you can also have access to various cluster dashboards here. And one of the cluster dashboards is the HD Insight cluster dashboard, which is, if you're used to Ambari, if you've ever used a Hadoop cluster with Ambari, this will take you to an Ambari page that will show you the health of the cluster. And there's a Yarn dashboard, which will show you how your jobs are progressing. Now, this is just to demonstrate. We're not doing this as part of the hands-on, but I'm just demonstrating. Okay, if you have, once you're an Azure user and you have a subscription, and there are free subscriptions available to try it out, you go to portal.azure.com, and that's where you would sign in with your subscription information.
But I assume the clusters that we built here are under all one subscription that's available unless we were to log into that subscription.
Right. The clusters that have been built for today's exercise are all under one subscription that was just for today's exercise. So we haven't given out the credentials for the subscription, just the credentials for the individual clusters. Okay, so let's go back to RStudio. Actually, that's taking a little while to log in, so let me go back to RStudio. And now the training and testing subsets of the data have been created. And let's train a logistic regression model on the data. So we're going to specify using R's formula language, R's normal formula language will specify our model. And our model in this case has quite a few predictors. The thing we're trying to predict is this variable ARR del 15, arrival delay of 15 minutes or more. That is to the left side of the tilde in R's formula language, and then everything to the right side of the tilde are the variables we're using to make the prediction. Things like month, because airline delay may be different in December than it is in June, carrier, and then the weather-related data. So we specify the formula of our logistic regression function, and then we call our server scalable logistic regression function, which is called rxlogit. So I'll just hit enter there, and the rxlogit function is now going to run. It will perform several iterations to fit a logistic regression model to the data.
The training data set and the test data set, are they physical data sets now?
The training and test data sets are now, you're saying, are they physical? Yes, they've now been materialized as physical directories of files in the distributed file system. Yes, yes. Mm-hmm. Another question?
Is there support for Carrot as far as an interface to work with many different developers?
Right. There isn't support for Carrot. Although, as we were talking about earlier, we do allow you to run essentially any R function in parallel. There's a distinction between running a function in parallel and parallelizing a function, taking a single function like logistic regression and allowing that to be a distributed algorithm. So we've written a number of the distributed algorithms, but we also allow you to run multiple copies of any existing algorithm across your cluster. So you could use this with Carrot as an example, where you ran Carrot. I've not tried this, but using what's called our rxexec function, which we'll be demonstrating in some of the other examples today, you could run Carrot, many different Carrot tasks across the nodes of the cluster. Yeah. Yes, to do parameter sweeps or to try a range of different models. Yeah, absolutely. So now the logistic regression has finished. And if we use base R's normal generic summary function, we can see information about the model that we fit. We see it took 7 iterations to fit. And we see actually these 3 stars next to all the weather data. So that's indicating that those are highly significant variables. And so it's good that we did join with weather data for this prediction. So now we're going to predict over the test data. One more question? What are the dropped variables? Okay. The model has some dropped variables. You see that destination airport ID is a factor, so each value of that factor, distinct value of that factor, is a term in the logistic regression, and some of those are dropped. Okay, so now we'll go on to the prediction. We're going to specify the XDF data file where we want to where we want to write the data that we'll be predicting, the scores that we'll be generating, and then we'll call the RxPredict function, which does the prediction. So the RxPredict function is now using the model that we generated with logistic regression to score the testing data. And once that's done, we're going to calculate an ROC curve and the area under the curve. And I can also execute those lines. And as soon as the prediction, the scoring is done, it will go on to doing the calculation of the ROC curve. So one thing I should mention is that we're using a subset of the data, as I mentioned earlier, and we have small clusters. We have 2-node clusters. A 2-node cluster is not really going to be significantly faster or even any faster than a single powerful machine because there's some overhead in using clusters. But the point is that we're using scalable functions that can run on 10 nodes or 100 nodes. That's where we would really see the benefit of clusters. So don't take the timing of a 2-node cluster with small data as really representative of what happens when you're applying this to the larger amounts of data that you would be encountering in a situation where you were scaling this to big data. So we can see that the ROC curve is now ready, and it's shown in the RStudio plot window. If you can click between files and plots if you're not seeing it. Now I'll move on to training and testing a decision model and a decision tree model. And the really only difference between training the logistic regression model and training the decision tree model is we use the RxDtree function now to do the decision tree model instead of the RxLogit function to do the logistic regression. And so you can go ahead and run the RxDtree function. And you'll see it will take several minutes because it's doing some cross-validation. It makes a number of passes over the data. But I'm going to show you something else. I'm going to show you actually how you can actually do local computing on the cluster if you don't have such big data. So I'm going to modify my version of the script just a little bit. And I'm going to copy some code in here. I'm going to set our compute context to local. And then I'll run that RxDtree function. So instead of using Spark, I'm going to bring the data to the edge node. So this just shows we have the flexibility of doing local computation in a cluster as well. And you'll see the output is a little bit different. Instead of it saying it's queuing a job and now a job is running, you just see us processing rows because it's just bringing the rows to the edge node. And this will finish probably faster than the Spark job. If you launch the Spark job on your computers, that'll take about 3 or 4 minutes. This will finish in maybe 1.5 minutes. Because we have a smaller data set here, really, in this case, it's more efficient to do local computation. And we could even speed up local computation further by copying the data to the edge, that so-called edge node. The data, remember, is starting in distributed storage, but we could use the Rx Hadoop copy to local to copy the data to local storage, and then it would run even faster. So these are just some options you have depending on size of your data. For example, sometimes in an organization, all the data is in the distributed file system. So that's why you're encouraged to use the Hadoop cluster. But not all of your calculations involve really big data, so that you might want to be able to pull the data from distributed storage to the edge node to quickly do a computation there locally. think that will finish momentarily. And then I'll also tell it to do the prediction and the plotting. I'll kick that off and see if I go to the cluster dashboard. I wanted to show you how you can monitor these jobs. Let me try that again. Try typing my password correctly. Okay, now I'm in. This is Yarn's list of applications that are running, and right now it says all the jobs are finished. So we are probably, yeah, we finished, everything finished actually. So we won't see any output there. But when one's job is running, one can click on the job and then drill into it and actually get into information on the details of the Spark computation. Once the job's done, that has to get copied to a more archival storage of the logs. So now let's go on to the third part, and I see I'm running a little long, so I'll try to speed up my covering of the third script, the deploy and score. Actually, this one is actually quite quick. So in script 3, we're all finished with script 2 now, hopefully. Moving along to script 3, we're going to, again, set the working directory, source the setComputeContext.r. Then we'll load the RxD tree model that we created in the previous script. I actually already stored the RxD tree model, the decision tree model, in your file system. So if you didn't complete script 2, it's fine. There's a pre-saved copy of the decision tree model that can be loaded by line 7. And now we're going to convert it from an open source R-part model, because for our scoring service right now, we're using pure open source R in this web-based scoring service. So I converted to an R-part model using the as_rpart function. And now I define a scoring function. So this is a function I'm writing entirely in R. It's saying library rpart, and it's calling the R's predict function on the rpart model. I'm writing it entirely in R, but I'm going to push this to a web service. So it's really easy to deploy without recoding in another language. We'll test out the scoring function locally. We'll take a little subset of the training data, just take the head of the training data, first 6 lines or so of the training data, and the first 6 lines of the testing data, and we'll use that to test out our scoring function here on line 30. As soon as we have the subset of data, we'll run the scoring function, and now you can see scores were written out. So these are predictions using using decision tree of whether we're going to have a delay or not. Now I'm going to publish this as a web service. So to do that, we use the Azure ML library, and line 38 will allow us to specify the credentials of our Azure ML subscription, our connection to what we call Azure ML Studio. And then line 40 really is the magical function, publish web service, where just by calling this R function, we're going to have a web service created for us. And it will happen almost instantly. When I run those 3 lines, the cursor's back. And now if I go to my list of web services in the Azure ML, I'm going to refresh this list. And if other people are also adding web services here, we're probably going to see a long list of web services, because everyone is adding web services to the same account right now. And once you add the web service, by the way, it takes about 30 seconds or so for it to become active. So if you try to predict immediately after creating the web service, you'll see it says it's going to wait. It's going to retry and wait a couple times. Interesting. I've never seen it not fill out that list. Let's try the link, this other link.
The web service, I noticed the scoring function uses the global environment.
Yeah.
So, is it
Yes.
the environment with it?
Yeah, it can bring some of the environment with it as needed. Okay, so let's try the web service that we created. We score using the consume function. This is an example of scoring from R, but you can be scoring from many different enterprise applications because it's just a web service. You just have to connect to a URL. So I'm calling the scorer function, and the first time you call the scoring function, it takes a little bit longer, but it's come back to the prompt now. If I type head of scores, we can see there are scores. So we've now taken our model and we've deployed it. It could be used now by hundreds of users because it is a scoreable web-based service. And you can turn off your R session now. Not for hands-on, but you could turn off your R session. You could shut down the cluster if you wanted to. That web service will still keep working because it's independent of the cluster. Yeah. How do we store the information?
Yeah, so like you just created a web service, but you say like other people can connect to it. How do you distribute that?
Oh, okay. Oh, yes, I should show you that. The list of web services didn't pop up here, which normally a list of web services will pop up in this window. And then if we click on the web service, there will be information about the API. It will tell you what is the API key and the URL to connect to the web service. Oh, here we are. Now it's showing. Good. So we see we have a lot of web services that were created by all of you just now. The date here, they're all showing today's date at 10/21. So if I click on one of them, now I can show you that API information. Okay, so I clicked on the web service, and here's the API help page for the request response service. You click there, and it will provide a lot of documentation about this API you've just created, including sample code. So it gives you some C#, Python, and R code that you can include in your applications to call the web service. Great.